So the questions have been uploaded to Blackboard, and you can take a look first, and we may start the discussion very soon. So I think we can start now. So let me share my screen. Okay, can you see the screen? Okay, so these exercise questions are basically related to accelerators and detectors. So for the first question, we are asked to find the magnetic field, which is needed to curve a 6.5 TeV photon so that it can keep moving in a circular orbit. So for this question, we can first write down the Lorentz force law. So the magnetic force is QEB, and using the Newton's second law and centripetal accelerations, you can then write down B equals P over QR, where P equals mv. And note that this relation is written in SI unit. And the second thing is that although we derive it by Newton's second law here, this expression also works in relativistic limit. So we can still use these relations for the relativistic photon. And I also noticed that in the lecture notes, the expression is written in this form, in which there is an additional speed of light here. And if you are confused, this actually written in Gaussian units. So, but for this question, we can just simply stick with SI units for simplicity. So we now have this expression, and you can just simply plug in the values. So for the momentum, since the energy of the proton is much larger than its rest mass, so we can just neglect the effect of the rest mass energy. And so the momentum will be just E over C. And so this is the momentum. And the charge for proton is 1 electric charge. And for the radius, we use the circumference of LC, and we can obtain the radius. And so substituting these numbers can get the B field is about 5.05 Tesla. And apart from using the SI unit, we can also handle these questions using the more convenient electron volt unit. So here the charge is 1 electric charge. So we first substitute these numbers in the denominator. And the things inside the square brackets is the unit carried by the variables. And then in the numerator, we multiply the value of the speed of light and then divide it again. So so this is the same as the previous one, but then we combine the momentum in SI unit with the speed of light, and then divided by the electric charge, and then the unit will become EV over C. Okay, so we further convert EV to GV, then we can get B equals P over 0.V R. So I think this expression is also mentioned in your lecture slides. So you can also directly use this expression and substitute P to be 6,500 and R to be 4,000, and you can get the same answer here. And if you check the web page of CERN, you can check that the actual magnetic field for the dipole magnets is about 8.33 Tesla. So it is a bit higher than our expected. And the reason is that in this question, we assume the magnetic field is evenly distributed along the circumference. But in reality, in XC, the magnets are not distributed evenly around the circumference. So there may be some other components, for example, the focusing lens. So the magnet is not distributed evenly. And so in order to achieve the same bending power, we have to use a higher magnetic field to bend the protons. So that's why the actual B field will be higher than our calculation. So we can move to the second question. And for the second question, we are asked to compute the thickness of a carbon in order to reduce the proton energy from 100 MeV to 50 MeV. So proton is a heavy charged particles. So we can calculate the loss of energy by using the curve of the specific energy loss. And usually the curve is very complicated, as you can see in the lecture slides. But here, since we are only considering a small range, so we can use a approximated form of the specific energy loss, which is shown here. So we can simply use this simplified expression. And the thing that we have to do is just integrate this equation. So we can first separate the variables and then integrate both sides. So for the left-hand side, we integrate from 50 MeV to 100 MeV. And on the right-hand side, the integration of x will be the thickness that we want to obtain. So you can just do the integration, and then we can obtain rho L to be 6.17. And here we are also given the density of carbon. And actually, here carbon refers to graphite. So the density is 2.27 gram per cm cube. So we can use this value and divide this number by the density. And then we can get the actual thickness in centimeters. So for the last questions, we are asked to find the highest possible KE of the proton that can be stopped by a bubble chamber filled with liquid hydrogen and also propane. And according to the hints, we can consider the lines for liquid hydrogen and carbon. So we can just use this curve. And the x-axis is beta gamma, which correspond to the momentum and the mass of the incoming particles. And for the y-axis is R over m, and actually refers to the range of the particles which can travel in the materials, and multiplied by the density of the materials and divided by the mass of the incoming particles. So we can consider two materials here. So the first one is liquid hydrogen. So because we are considering the highest possible KE, so we can just set the range to be the diameter of the chamber. So here we just convert the unit from feet to centimeters by this factor. So this is the range, and the second term is the density of the material. So you can just search on the website. So the density for liquid hydrogen is this, and the density for propane is like this. And lastly is the mass of particles. And so we just substitute the mass of proton. And so we can get the value of R over m. And the tricky point here is that the curve is drawn in log scale. So it is not so trivial to locate these numbers on the y-axis. So for me, I just simply use a ruler to help me figure out the position. So I first measure the length between 1 and 10. And for me, I just measure 3.8 cm. So and then I multiply the length with the log of the value. So here for liquid hydrogen, R over m is 27.6. So I just calculate log 27.6 and then multiply the length that I just measured. And the result is 5.5 cm. So I measure 5.5 cm from here. And so this horizontal line will correspond to 27.6. And so just draw a horizontal line and to meet with this liquid hydrogen, and then we can obtain the value of beta gamma to be 0.9. And similarly, for propane, we have to figure out 192 on the y-axis, and I just use the same method. So I just measure 7.3 cm from here. So this is the horizontal line correspond to 192. So I draw a horizontal line from here to the carbon line. So I just get the beta gamma to be 1.35. So now we have got beta gamma for liquid hydrogen and propane. And so we can obtain the momentum of the proton. So beta gamma is just P over mc. So we can just multiply by the mass of the proton to get the momentum. And from the momentum, we can get the total energy by using the energy momentum relation. And finally, we can subtract the rest mass energy from total energy to get the KE. So this will be the highest possible KE that can be stored by the chamber. So that's about the exercise questions. And seems that we still have some time, so I can talk more about this expression. So I just said that this expression is also valid in relativistic case. So I want to give a brief idea how to do it in special relativity. But it's not a rigorous proof. It's just a simple demonstration how to do it without using the classical Newton's second law. So in relativity, we don't want to use F equals ma, but these two equations are still valid. So the magnetic force is still QV cross B, and F equals dp dt is also valid in relativity, given that the momentum is relativistic momentum. And but note that these two equations can only work in the laboratory frame because they are not written in four-factor form. But it's enough for us because we are working in the laboratory frame. So, so these are the two equations that is also valid in special relativity. And since the magnetic force do not do work, so the particles momentum will not change its magnitude, but can only change the directions, and the force will also be perpendicular to the direction of motion. So the particles will still move in a circular orbit. So we can consider the momentum change of particles. So assume the momentum is P here. And after some time, particles momentum will be P prime. So it's something like this. And we can assume the angle here to be delta theta. And by simple geometry, you can see the angle between the two momentum vector is also delta theta. So this will be the momentum change. So the momentum change will be the magnitude of the momentum multiplied by the angle, and direction will point to the center of the circle. And because the particle is doing uniform circular motion, so delta theta delta t is just the angular speed and is equal to v over r. And so using these relations and substitute back to these previous relations, we can get delta p delta t to be pv over r and pointing to the center of the circle. And if you just let delta p and delta t to 0, and you just become dp dt, and dp dt is just the force, so it's just qvb. So the magnitude, so qvb will just equal to pv over r, and canceling the speed v, we can just get back b equals p over qr. So that's a simple way to obtain the same expression without using F equals ma. So that's why this relation is also valid in relativity. Okay, I think that's the end of the exercise section, and you may leave if you have no questions. And if you have questions, you can ask. My C line corresponding to propane. So because so the main atoms in propane is carbon atoms. So that's why we use carbon lines.
But there are more hydrogen in propane than carbon.
Yeah, I know, but let me see. Yeah, you're right. There also hydrogen, but I think for example, we can consider because carbon atoms is has a larger mass than hydrogen atoms, so we can just ignore the effects of the hydrogen atoms.
But this curve, as it was explained in the lecture, the differences between different material, different elements is mostly because these substances, they have different densities. So by using, by stating that you can use the C line for propane, that would imply the propane has a similar density as to C, which it depends on the form of carbon will have different density. So which form of carbon is it actually in this, line in the graph?
Yeah, then you can just change the density here.
No, what
For
I'm
example,
saying
if
is
you
that
if you
the
don't use
graph,
propane, if you just use other gas, then you just change density here. But the main atom is still C, still carbon.
but propane is saying C3H8, I think. There are 3 carbon in it. So for each propane molecule. So why is it? I mean, even if it is carbon, it would be 3 carbon, not 1 carbon.
Let me think about it. I think it doesn't matter whether it contains 1 carbon or 3 carbon because so the meaning of this curve is just to so we just have to consider the type of the atoms. It doesn't really matter whether the molecules have 3 carbons or 1 carbons. So suppose, for example, here for previous questions, we use I say the carbons actually refers to graphite, and we can still use the same curve here because the atom is carbon. It doesn't really matter the structure of the material or how the atoms are linked. So,
but what I'm thinking about, so my understanding of this curve, the reason we have this curve is because the electron or whatever, in this case, proton, it impart its energy into the molecule or the atom, or in this case, carbon. And so the energy is lost because the proton bombard with the carbon atom and loses energy. Now,
yes.
however, with a propane molecule, it can bombard with the carbon, but it can also bombard with the hydrogen atom. And in fact, the entire propane molecule is surrounded by hydrogen molecule. Then I would imagine it has a higher chance to bombard into a hydrogen atom than a carbon atom. Then, yeah, I would expect, yeah,
Well,
I would
then,
expect a different curve.
yeah, you can also include the effect of hydrogen, but I don't know, I don't know whether that will be well, you have to do some more complicated calculation to compare the effect of carbon atom and hydrogen atom. But I think the effect of carbon will dominate because well, you have to consider the energy levels. For example, carbon, I expect it has a higher ionization energy. So when the proton bombard with a carbon atoms, it's easier to excite the carbon to. But for hydrogen, it will just ionize the hydrogen, and it will not cause a large energy loss for proton. That's just my guess. So I think that's why the carbon lines will dominate over the hydrogen. Yeah, you are right. For accurate calculation, we need to differentiate between different molecules. But here, I think we can just assume that the carbon atoms dominate the effects.
All right. The other question I have is when you said we can derive the equation for the momentum,
yeah,
without using F equals ma. There you use F equals the change in momentum, the rate of change of momentum.
yes.
That one you would need the proper time, right? For in the relativistic case,
this is still valid, given that the P is the relativistic momentum, and the proper time is for the full momentum. Is for the four. Not if you use proper time here, then the left hand side will become the 4 force.
But
here we can just simply use this because we are stuck with the laboratory frame.
But if I remember, if my memory serves,
yeah, you can also write something like this, where P will be a 4 momentum. This is a proper time. Then this will be a 4 force.
No, but I tend to remember in the relativistic case, if you don't use the proper time, but like just a t there, then you would have an extra term due to relativistic effect for the force, right?
I don't think so, because the P is already contain, the P is already gamma MV.
Okay.
Yeah, you can have a check.
Okay.
The last question, why P equals beta gamma? Okay, so we are talking about this. Okay, because let me see. So beta gamma, you can just refer to here, because beta gamma is just beta is V over C, and gamma is the 1 over square root 1 over 1 minus V square over C square. So after simplifying, it will be just momentum divided by the mass and the speed of light. So this is P equals mc. And you can just multiply C so beta gamma times mc square will just be PC. So we can just obtain the momentum by multiplying beta gamma and the mass. And the reason that to multiply C is to just so that we can use MeV unit.
Can I ask a rather silly question? When you have a proton beam shooting to a carbon, like a graphite plate or something, will it burn a hole, or will it cause the carbon to combust, or will it do anything to that carbon plate? Is that essentially, will it, after you do the experiment and then you take out the carbon plate, will it have any visible effect, like any visible traces or something on that graphite plate? I'm referring to question 1.
I guess it will not cause effect like combustion, because a single proton beam doesn't have so much high energy, because if you convert the energy from MeV back to joules, you will find that the energy is in fact much smaller than the energy, the chemical energy that we encounter in our life.
But I thought the proton beam is not one single proton, right? It is a continuous source of proton shooting towards the carbon plate. So when you accumulate all those MEVs, wouldn't it have enough energy to burn a hole or something?
That's quite hard to say. Yeah, I'm not sure.
Never mind.
I don't think so, but because yeah, if that's the case, then yeah, I'm not sure.
Okay. Just one more thing. When you in the second question, we have the energy loss rate. Why is it in a power law? Like, do we have any reason? In physical intuition, why is it a power law to the energy? And why is it such a strange exponent, like 0.757? Is it just a curve that you get from regression? And then you just randomly fit a power exponent to it, and yeah. Or is there an analytical form from it for it?
For the analytical forms, it is you can see the lecture slides. There's actually an analytical form which can derive from the principle of quantum mechanics. But here, for the simplicity of calculation, this is just an approximated form to the curve that we have. That means so it is only valid in this energy range.
Oh, so the analytical form is a rather complex curve.
Yes.
And within this range, you can use this power law to fit it.
Yes, and why is power law? I think one reason is that it's easy to do the integration.
Okay.
Yeah, I think there's also other approximated form that we can use. So this is just one form that can describe the curve in this energy range. So I think there's not much analytical reason.
Wait, hold on. If you have a curve and if you confine it to a certain range, then I would imagine, if you just randomly think of something to fit with that curve, I would imagine a Taylor series or something. But for a Taylor series, you would start from x equals, the exponent starts from 0, and then 1, 2, 3, 4, 5, and it goes on. You wouldn't start from a fractional exponent with a negative sign. So I was thinking, like how do you get this approximation form? Why would you start with this approximation?
Well, if you just use Taylor series, then you are just using the same. You are just see. So you are saying that why we are not using another form, for example?
Well, okay, there are many other forms, of course, but I was just thinking, why do we? I mean, is there a reason why we use a power law to approximate it? Because I mean, intuitively, I would use a Taylor series to approximate the curve instead of a power series, a power law like this. Like, where does it come from in the first place?
So what do you mean by Taylor series? What? You mean
The Taylor series means the Taylor
the-
expansion, like x0, x to the 0 power plus x to the first power plus x to the second power plus x to
yeah,
the...
you can also do it in this way. So you can just use a polynomial
Yeah.
in
The
the right hand side.
polynomial, but here we use a power law. This is what confuses me. Like, why would you use a power law in the first place? Is there something in the equation that pushes you or guides you to use this power law instead of other approximation series like a Taylor series or some other funny series?
Okay, I see your point. Okay, maybe I can check more to see where there is an theoretical reason. And at this moment, I don't know much about this form. Maybe so I can check and answer you next time.
Okay,
yeah.
No problem. Thank you so much.
Okay. Any other question?
No.
Okay, so
thank you. See you. Bye.